Hi, my name is Amir Ghasemi, professor in operative dentistry with more than 35 years of experience. Today I will be talking about 3D printable permanent material and compare them with conventional methods. Nowadays, digital dentistry has become very popular. This has made 3D printing in dentistry possible. Marketing companies show growth in hardware, material, service, and software marketing also. CAGR, one of these analyzers, predict more than $7 billion growth in 2030 in dental 3D printing market. Other market analysts forecast even more growth. It is expected that the 3D printing market will rise by 20% in North America, while in dental 3D printing it reaches about more than 26%. Furthermore, percentage of consultants using 3D printing was doubled in 2 years. It is estimated that 96% of dental labs with more than 5 employees use 3D printer. The expansion of 3D printing in dental lab is expected to continue with compound annual growth rate of more than 26 from 2023 to 2030. Surveys indicate that 3D printing is mostly used in model, spline, surgical guide, aligner, and provisional. Since 3D printed material like composite, ceramic, and metal are improved, they find their own role in dentistry, especially in Asia, Europe, and North America, respectively. Article in the last 5 years show most used technology have been vat photopolymerization, material extrusion, material injection, and powder bed fusing. And the most popular material are zirconia, glass ceramic, and composite, which have been used as a crown, bridge, implant, and a research in PubMed also showed the same increase in number of articles in the last 3 years. Printable dental material are classified based on various aspects including clinical structure, tissue compatibility, application and mechanical properties, printing technology, and their final performance. For example, resin, ceramic, metal, or composite are subgroup of composition title, or orthodontic surgical guide, restorative material are division of application, but today we will classify them by uh, application and by function as permanent or temporary in the month. We will mainly discuss and evaluate material that are most often used as a restorations or permanent prosthesis. As you know, the field of dentistry has found many use of printable materials, and the scope of these use are increasing every day in a way that has become similar to an iceberg. Accuracy, repeatability, speed, cost effective, improve engaging patient experience, and better communication and education are some of reason and benefit of this widespread of use. However, initial cost and maintenance are high. This system requires special skills. There are still many material limitations, and most of them require post-printing process. They require continuous control and calibration to maintain accuracy. These There aren't sufficient regulation and permit yet, and of course the size and space required for device and are currently considered to be limitation and disadvantages. What the facility and convenience which are provided covered all disadvantages. Perhaps mention some of facility provide a better clinical approach to this lecture. The study shows uh, that loosening proximal contact around implant is a common problem with implant crown. Printable composite crown with ability to directly and indirectly repair are one of the solutions to solve this problem. Moreover, reducing occlusal stress caused by the flexibility of printed composite also reported. Digital dentistry or printing the complete or partial mold and matrix immediately allow for fast and beautiful vinyl application even for dentists with less artistry and skill. Since printers technology has been introduced by industrial company into dentistry, 3D printer dental material also being developed by them. However, these companies are not familiar with dentistry. Sprint Ray, Shining, PackDent, NextDent, Siga, Formlab are in these groups. Although recently some of well-known dental manufacturers will like Dentsply, Bego, Soremco has been involved. Today I speak mainly about printable permanent restorative material consists of composite and ceramic, which some of them are shown here. Ceramics group and composite resin groups. First I am going to talk about composite part. Warsaw Smile from Bego, permanent crown from Formlab, crown tech from Saremco, ceramic crown from Sprint Ray, or some of them. Oskan and Zandi state that there is very limited information regarding chemical composition and mechanical properties of additive materials. 3D printable composition need to complete evaluation as well due to different raw material, processing and curing or sanitary. This situation in 3D denture resin are more complicated, related to so many different range of material which are used uh, and found in these compositions. It is more interesting to know that about 20% of composition belong to additive that was not found previously. In the field of permanent material, properties such as physical and mechanical properties will be evaluated, like flexural strength, color, surface properties, viscosity, dimensional accuracy, shrinkage, and etc. Well, viscosity is one of important properties and limitation. 3D printer need minimum viscosity for optimum performance. On the other side, with increase in loading of filler for better mechanical properties, viscosity increased dramatically. Even in powder fusion technique, which uses powder, not slurry, for printing, flow is very mm, flow is very important factor for printing. In terms of viscosity, printable material are divided to three categories: low, medium, and high. Its unit is centipoise, ranging between 100 to 2500 in 25 degrees of centigrade. Viscosity plays a critical role, especially for DLP and SLA printer, which low to moderate viscosity resin are common and its requirements. Their importance is explained by adhesion and recoating ability of the resin to avoid defect and void, and obtaining good mechanical properties. Because of this limitation, some of the printer, the bottom of VAT, the bottom of VAT film of printer is flexible to prepare close adaptation, to prepare close adaptation and elimination of void and defect. No comparing with dental flowable or conventional or packable composite viscosity which approximately range of 2000 to 90,000 centipoise. You see value of Filtex Supreme and Grandio, which are high viscosity, high filler, and high strength compared with printable resin. Fortunately, in this upper temperature, viscosity drop severely. Therefore, some of mm, wet printers have added a heat generator. Surveys confirm the positive effect of uh, heated wet on strength, but we should be aware of accuracy. Now, in aspect of manufacturing dental composite versus printable composite material, they have a similar structure such as monomer, filler, coupling agent, initiator, and etc. Only the portion of component are different. For example, percent of filler is lower in printable composite material, which shows one of their biggest difference. In printable composite, there is about 3 to 50% filler, but strength may be affected by resin composition also. It means this amount of filler is very low. As shown, the viscosity and stiffness of BCMA, UDMA, BCMA, and TEC demo decrease respectively. In dental composite, we can see that there are more of the high viscosity and stiffness monomers. However, in printable dental composite, this order is reversed. In evaluating some of the other properties of 3D material, we will talk about shrinkage. Shrinkage is usually from 1% to 5% depend on resin formulation, even 0.1 for metal and 90 to 30% for zirconia. Whereas printed material are similar to indirect restoration and shrinkage take place before cementation, a slicing software can mathematically compensate this value manually or automatically. So this is and a big problem. From the regulatory point of view, most of the introduced material to market have CE and FDA certification and approval. Both regulation and standard rule for this material are new and have not been completely covered yet. For better understanding of exact chemical composition uh, of printable composite, we evaluate the safety data sheet. Varseos Micron Plus present 50 to 70% of their own product with complicated formula, but in reality this is nothing but base EMA. It means that its actual viscosity and stiffness is lower than dental composite, particularly when we know filler amount uh, is less than 45%. Second and third row are methyl benzoyl and TPO UV initiator, which mostly common in 3D printing dental materials. Sculpture present this case number. which belong to 3-ethylene glycol dimethacrylate, a thinner monomer mainly used as a cross-linker and thinner. So it is possible to have even more than 60% of filler, but we know that resin is extremely weak. Chromtech Saramco also has this EMA. Flextra Desktop has low viscosity methacrylate. All of these indicate the possibility of less strength compared with conventional composites. Moreover, we saw that wavelength of initiator of 3D dental printable material are mostly in the range of UV. The reason for this that come from industrial background and the UV initiator technology has been an established and mature process known for wide ability, low cost, suitable curing speed, high resolution, and high energy due to lower wavelength. Now see the other manufacturing process competitor of uh, 3D printing material in the name of indirect composite or CAD/CAM block, including lava and katana. In contrast with direct composite, manufacturer of this competitor has not mixed filler with resin initially. Filler are pressed in a mold in one step or two. Oil or gas is used to reach very high isometric pressure. Then this compact filler with the name of green body is infiltrated by resin. To achieve this, after uniaxial press, after uniaxial press in this mold, green body is embedded in a plastic shelf, then subjected to cold or hot isostatic high pressure. Sometimes polymerization is done in high heat and high pressure, which is not comparable to 3D printing post-processing. As shown in this slide and next, they show positive effect of high heat and high pressure on mechanical properties of the composite cured disc. This picture shows pressure and heat chamber. Nowadays, argon gas is commonly used as media to increase this uh, isostatic pressure and heat because argon is inert. Now let's understand how big 200 megapascal is. It is better to see the pressure in a dental autoclave. One of the best post-curing methods of direct-indirect composite As we all know, pressure in autoclave is 122 bar and heat is around to 126 degree. Whereas in manufacturing hybrid ceramic, it is necessary to have a pressure of around 200 megapascal equal to 2000 bar. It means 2000 times bigger. This level of pressure is below the capabilities of current printing post-processing technology. Recently, Edelweiss introduced composite veneer and only created an in high heat, high pressure molding and additionally laser sintering as well for this type of restorations. Positive, positive effect of pressure and compaction appear in new 3D printer of sprint ray in the name of Medius, but still the pressure is very low and not enough. Systematic review in 2025 confirmed the lower mechanical properties of 3D permanent resin restoration. Some researchers believe that 3D printable composite are acceptable for dental prosthesis in posterior area. If we read their result, we see that they have more than 30% failure only in the first 2 years. Only in the first 2 years. I won't consider this value acceptable. In evaluation of other study with acceptance conclusion regarding 3D printed material, we observed two subtractive hybrid composite and one subtractive methacrylate-based material as a standard group for compare. Whereas this selection only present the weakest in the subtractive base material. Today, lithium disilicate for non stress bearing area and zirconia are, uh, are the clinical choice. Even subtractive groups show significant even subtractive groups show significant increase in fracture strength after aging. Promising is a better word to describe when we see lower mechanical properties as revealed in this paper when we are in a range of lower mechanical properties like fracture and fatigue strength. This paper and the next one indicate lower strength for printed composite material, lower fracture and lower strength. They report that these materials cannot be alternative to milled. As I said before, this article also confirms 3D printed composites have lower mechanical characteristics than hybrid ceramic and glass ceramic also. Article. In agreement with previous paper, increasing order of mechanical properties of printable composite, direct composite, hybrid ceramic, and glass ceramic have been reported. Finally, postodontic literature concludes the lack of evidence for 3D printable material as a permanent restoration. Printed permanent restorations or material need for post-processing. For this point of view, comparable with indirect restoration, washing, curing, polishing are involved in post-processing, but we focus on curing. All mentioned methods in this slide are different ways of the post-curing, like oxygen inhibition with nitrogen-rich space, thermal chamber, light chamber, intensive light, and increasing even heat, or combination of these methods are also used. Since printers work with low intensity, polymerization is incomplete after printing. Therefore, post-curing improves degree of conversion, micro-hardness, and stainability. But in comparing intensity of dental light cure, we can see clear difference between each other. Time and temperature are important factors regarding flexure and color of the printed permanent crown. The articles show verify to this fact. This systematic review indicates nitrogen-rich post-polymerization does not significantly alter the physical, chemical, or mechanical properties of the 3D printed dental material except for high degree of surface polymerization. More than 20 years ago, when I was young, and when indirect composite restoration was a hot subject in restorative dentistry, even with severe post-curing, significant clinical difference was not detected. Recent research still confirms this finding. While the post-curing process in indirect composite, which has a higher temperature, pressure, and intensity, does not have much impact on their clinical success compared to direct composite. In your opinion, this will be evident in printable composite. If addition lower filler percent and less stiff resin of printable composite materials. Now, what's your response? Unfortunately, 3D printed restorations exhibit clear discoloration over time. Additionally, we should know increasing material thickness was found to be correlated with increased yellowness in the sample. The discoloration of 3D printable dental material make them transform to darker, more yellowish, and more opaque color after 6 months of water storage. Milled material, particularly ceramic, demonstrated superior durability and aesthetic retention. Optimization is needed for 3D printed resin material to enhance their mechanical and aesthetic properties for long term. Applying treatments such as varnishing, coating, and polishing can improve the color stability and surface properties. Yet it isn't enough. Orientation of 3D resin printing influences translucency and aesthetic, which is shown in this article. 3D printer resin are affected at different levels by coloring solution, micro hardness, and flexural strength of 3D printed sample kept in a different coloring agent are different. Interestingly, if the 3D printable material that hasn't been printed and only cured wouldn't encounter any problems, so manufacturing method of the printer is not very important. Printable glass ceramic is the second permanent product that we will discuss about after printable composite. Number of commercial printable product of glass ceramic is very limited. Lithos Incorporation with Vivoden recently introduced one product. These are some of the commercial methods of manufacturing glass ceramic or lithium disilicate. Our colleague prepared one experimental glass ceramic. Raw material were weighted and put in a furnace. Temperature was increased till 1500 degrees. After 2 hours the melt is quenched in water or molded. Vivoden has similar procedure of remelting and heat treatment and change the glass to glass ceramic, then ball milling and particle size reduction process is applied. Then hot isostatic pressure is used to manufacture the CAD-CAM partially sanitary block. Therefore, our glass ceramic restoration are manufactured in high temp and high pressure. But a common experimental method of fabrication of printable lithium disilicate is schematically shown here, which is similar to conventional procedure after melting, quenching, ball milling, coating the particle with dispersant. Sometimes binder and ultraviolet resin are added. Experimental slurry contain about 30% additive for reaching the printing requirements. These research obtained 90% density, 350 megapascal bending strength, and 2.9 toughness. Other printing technology like robocasting cannot reach cannot reach the strength of conventional glass ceramic yet. Major advantage of 3D printing lithium disilicate by using LCM method is obtaining ultra-thin restoration, which is very difficult to achieve in conventional method. On the other hand, an important disadvantage is prolonged and sensitive debinding method, about 5 hours. Glass ceramic generally exhibit a density of 2.5, Vickers hardness 6 to 7 gigapascal, fracture strength typically between 3 and 400 megapascal. And in this research, with decreasing the resin portion and increasing the glass ratio, they can only reach about 170 fracture strength. The method 3D printing of ceramic is expanding more and more every day. Filament fuse deposition is a simple and well-established method which is currently available for lithium disilicate. In comparing printable and conventional glass ceramic, I should say in terms of fitness and aesthetic there shouldn't be any problem. Regarding to strength, conventional methods are supported by a strong data and document, while 3D printer does not have enough data. As I mentioned, 3D printing may be preferred for preparing thin restoration. Finally, we are going to discuss zirconia. Zirconia is a key material in subtractive manufacturing. Interestingly, the same consideration for its attention and consumption are becoming relevant in the world of the 3D printing of the dental ceramic. We all know after preparing the zirconia stabilized by yttria powder, which is mostly nano-size, it is packed uniaxially in a mold, then the green body is vacuum packed in a thin shield and subjected to cold isostatic pressure, about 100 to 300 megapascal. Then the placenta in about 1000 degrees of centigrade. Sometimes between these steps, powder is mixed with binder and additive, dry and then ball mill. Sometimes even slurry and granule are applied for better surface quality and packing. Finally, as shown in this slide, ultra-high isostatic pressure is applied. One of my colleagues has done these steps. In spite of the high attention to zirconia, there are only a few commercial products in the market with very limited limited scientific documentation from manufacturing. Simple schematic view from this process is shown here. Completely dry powder is mixed with dispersant in alcohol, then dry and mill again, mixing with photocurable resin even as long as 24 hours continuously to obtain a homogeneous slurry. Of course, particle size is important and as it affects several properties of final product. Several different materials are used as a dispersant in this process. Binders are specially used in robocasting and direct ink writing methods. Monomers and polymers along with initiator-activator system are involved in processing the slurry to create primary geometry and shape of the 3D printed prosthesis before final sanitary. As mentioned, existence of light cure resin, additive dispersant, and etc. is necessary for preparing of stable slurry in printable zirconia material. Both long and sensitive debinding and sanitary consist of 20 to 30% shrinkage procedure and can take from 20 to 100 hours. These problems lead to delamination, crack, and void. Investigators are examining different methods of printing zirconia, each with own limitation. Furthermore, zirconia inherent properties can create some problem like high melting point, high density, high opacity, and high specific heat. High reflective index tend to poor cure and the reduction of resolution. The differences in the raw material and their method of processing, whether using selective laser sintering or selective laser melting, complicated conclusion. In terms of obtaining density, printing is successful or very near to success. But on the other hand, density of zirconia can lead to precipitation of printing sludge. As I and several articles mentioned before, the accuracy is acceptable in the printable zirconia. Some researchers believe that there is still a long way to go in order to include additive manufacturing technology in dentistry. In some articles, the mechanical properties of zirconia are so low that we won't talk about it. Some claim that there aren't clinical studies yet that would indicate the use of ceramic for permanent restoration. Others show that a step-by-step increase improve flexural strength and density to level near to subtractive method. They also show that printing orientation affect mechanical properties. Two demonstrated papers show approximately equal mechanical properties with subtractive method. However, it should be noted that the first study, the average strength was numerically lower, but not significantly. And in the second study, they were compared with zirconia with 5 mole of yttrium, which is inherently weaker than zirconia with 5 mole. Due to the higher light reflectance index and density of zirconia, which accelerate sedimentation and make the curing pool, having only 40 to 60% zirconia in slurry of printable, existence of different dispersant and additive which should be removed before centering, long and sensitive debinding with incomplete reference and a lack of very high pressure are used in make of CAD/CAM. Now you can make the decision. Finally, thank you for your attention. I hope that this presentation will help you in your dentistry journey.